So hello everyone and welcome to today's lecture recap. And so I'm going to start by talking about what we did last time. And that was to understand why it is that heat always flows from the hotter object to the colder object when we put two objects in thermal contact. And this is related to the question of why we can't build an engine with perfect efficiency, and related to the question of why we always need to provide work if we want to make a refrigerator that takes heat from a cold reservoir and puts it into a hot reservoir. And so the basic mechanism here, it turns out, has very little to do with the detailed physics of molecules and energy and so forth. The basic mechanism for understanding why heat always goes from hot objects to cold objects is the same as the way we can understand why, for example, in this scenario, that the candy wrappers at the end of the night here are scattered over a large area on the floor rather than in a neat little pile like how they started. And the point is basically just that in this situation here, there are so many more possible configurations where the candy wrappers are scattered all over the place compared with configurations where the candy wrappers are in a neat little pile, that if we have sort of a random process that determines where each individual candy wrapper ends up, so if we're not really careful to make a neat little pile, then it's just an extremely low probability that all the candy wrappers will end up in a neat little pile. It's much more likely that you'll end up in one of these more common configurations where the candy wrappers are spread out. Okay, so sometimes people talk about the fact that things ending up messy is because of an increase in entropy. And it's true that that mechanism is the same as the mechanism, the reason why things end up messy is the same reason why heat flows from hot things to cold things. And I'm going to review that now. Okay. So, so we want to understand these various questions. And in last lecture, we started by considering the example of a simple model where instead of heat and energy and molecules, all we had is a configuration of frogs where the frogs were programmed to individually hop around completely randomly, taking a hop in a random direction at each time step. What we observed in the simulation was that there was always a net flow of frogs from the region where you had a higher density of frogs to the region where we had a lower density of frogs. So starting with a configuration like this, with say, I think we had 10 frogs on one side and some large number, let's call it 90 on the other side. We never observed this, and we could run the simulation for the rest of our lives, and we'll never observe the situation where all of the frogs end up on one side. Every single time we do it, if we wait long enough, we find that it tends to the situation where you have an approximately equal number of frogs on the left and the right. So we always see a net flow of frogs from the higher concentration to the lower concentration, even though those individual frogs are moving around randomly. Okay. So it's possible that they could end up moving all to the right. So why don't we ever see that happen? And it's basically because if we count how many possible configurations there are like this configuration, so we count, say, how many configurations are there where you put 100 frogs on the right-hand side. Turns out there's about 10 to the 500 configurations like that. So that's assuming that there's 10 to the 5 possible pixel locations for each frog. This number is just the number of ways of choosing 100 things out of 10 to the 5 possible locations. So that's a huge number, but it's a tiny number compared to this other number here, which is the number of configurations where you have an equal number of frogs on the left and on the right. And so there we would want to count the number of ways to choose 50 out of 10 to the 5, and then multiply that by the number of ways to choose 50 out of the 10 to the 5 on the right, and that gives you this number. Okay. And so what that means is that if we start here and then we let the simulation run for a long time so that we end up in some kind of random configuration of frogs, it's 10 to the 30 times more likely that we'll get a configuration like this one with an equal number of frogs on both sides compared to a configuration like this one with all the frogs on the right. So this particular configuration on the left is no more or less likely than this particular configuration on the right. It would be just as likely to end up here as here. But if we think about the probability of ending up in a configuration with 50 frogs on the left and 50 frogs on the right in any kind of arrangement, then that is what's so much more likely. So we've understood why it seems that the frogs always flow from the region of higher concentration to the region of lesser concentration. It's just because when you allow the random processes to happen, you're much more likely to end up on one of these common configurations compared to one of these relatively rare configurations. So it's just a question of probability about how many configurations are like the one on the right compared to the one on the left. Now we can directly apply that argument to the situation of heat flow when you have a pair of objects together. And so it's a perfect analogy in that the frogs in our simulation, they were moving around randomly and they were conserved in the sense that we always had the same number of frogs. And so that's the same with energy. When we have various molecules in a solid, then energy can be transferred between the molecules through their interactions, through the collisions of nearby molecules. And so if we imagine that there's a bunch of different units of energy, then these units of energy essentially are moving around randomly, just like the frogs. And the energy is also conserved. And so we can understand that the process is very similar to frogs hopping around randomly in the simulation. The temperature, remember, that's related to the amount of energy per molecule. And so in our analogy, the density of frogs, so basically the number of frogs per area here, that's directly related to the temperature. And so we could say that the heat always flows from the region with higher energy density, meaning higher temperature, to the region with lower energy density, because the number of configurations with equally distributed energy on both sides is vastly greater than the number of configurations where most of your energy is on one side. Okay. And so if we start here in this situation with 20 degrees and 80 degrees, we're always going to end up going towards this situation where the temperatures are more balanced. And we're never going to end up going towards this situation where the temperatures are less balanced, because there are so many more configurations of molecules where you have the temperatures being 30 degrees on one side and 70 degrees on the other side, compared with the number of configurations where it's 10 degrees on one side and 90 degrees on the other. And the numbers are even more different, but compared to comparing one side to the other than in the frog example. So it turns out that if you actually calculate a measure of how many relative configurations there are like this, how many configurations of molecules have these temperatures versus how many configurations of molecules would have these temperatures, then it's this many times, I don't even know how to say that number, it's this many times greater. And so you're that many more times likely to end up here than to end up here if you start in this configuration and then let energy be transferred by these random collisions of molecules. So this is the heart of what we call the second law of thermodynamics. It's just the statement that some events have just a far, far, far greater probability, so much more that you'll never see the other alternative happen. So to be a little bit more quantitative about that, we defined the concept of entropy. And that was just directly related to the count of these configurations. So entropy is a property that we can assign to some macroscopic configuration, meaning if you say there's 30 frogs on the left and 70 frogs on the right, we can associate an entropy to that situation. And it's just related directly to the number of configurations with those numbers of frogs. More precisely, you actually take the logarithm of that number for reasons that I'll explain in the next slide. Okay, so this is the definition of entropy. You look at your macroscopic variables. In the frog case, that would be how many frogs on the left, how many frogs on the right. You count the number of such configurations, and you take the logarithm, and then the entropy is some constant times that number. For the molecules of, say, a gas in a cylinder, in this case, what we mean by macroscopic variables would be our pressure, temperature, and volume of the gas. And so given a certain pressure and a certain volume and a certain temperature, then there are many, many possible ways that you could have molecules with those macroscopic variables. And again, the entropy is a measure of how many such configurations you have. So you take that number, you take the logarithm, and the entropy is some constant times that. Okay. Just as a really simple example about what we're talking about when we're talking about these microscopic configurations, at the bottom of the screen here, I'm showing some examples of microscopic configurations where you have 0 frogs on the left and 5 frogs on the right. There's an extremely large number of these configurations, but we can basically just we can just count them mathematically. It's the number of ways of choosing 5 locations out of 100,000 possible locations. Okay, so with that definition, then we can state the second law of thermodynamics, which is that the total entropy never decreases. And it's a really simple statement. It's then just the statement that allowing the random processes inside your material to happen, you're always going to end up in the configuration where there's a higher entropy. And that's just saying that there are vastly more configurations similar to this one than to this one. And so probability tells you that you're always going to end up here. And when I say always, I just mean, well, again, this many more times more likely. And so that means in reality, if you do it as many times as you could in the whole lifetime of the universe, you're never going to expect even one time to end up here. Okay, so it is a probability statement, but it's so much more likely that we just call it a law and we say you will never see it. It'd be like winning the lottery a billion times in a row. Probably even more unlikely than that that you would go to this side. Okay, so that's our second law. And it's interesting to understand the microscopic origin of it. But later when we're actually doing calculations, we won't really have to refer to this definition of the entropy being the log of the number of microscopic configurations. We're actually now going to present a macroscopic way to calculate entropy changes and entropies. And that's the thing that you'll actually need to use in various problems. Okay, but it's important to really understand what entropy is. And it's really coming from this sort of numerical or combinatorial or statistical definition. All right, so let's talk about some properties of entropy that we're actually going to use in our kind of more practical calculations. So the first property is that entropy is an additive quantity. And so if I have a system with two parts, then just like energy, we can say that the entropy of the total system is the entropy of the first part plus the entropy of the second part. And this actually has to do with the fact that we defined the entropy in terms of the logarithm of the number of configurations rather than just the actual number. And so I'll quickly just give you an argument for why the presence of that logarithm means that entropy is going to be additive. Okay, so imagine that we have, say, a pair of dice, and we roll a pair of dice. And so you could say that the number of possible configurations of the left dice is 6. The number of possible configurations of the right dice is 6. Die is 6. And the number of total possible configurations is 6 times 6, or 36. And so more generally, when you have two different parts of a system, and each part can have a certain number of configurations, then the total number of configurations of the whole system is just the product of those two. For each configuration of the first one, you have, say, n2 possible configurations of the second one. And so the total number of configurations of your system is n1 times n2. So when we go to calculate the entropy, given some macroscopic variables here, say the temperature of this object, and then some macroscopic variables here, the temperature of this object, then the total number of microscopic configurations consistent with that would be the product of the number of configurations on the left times the number of configurations on the right. And the entropy then is proportional to the logarithm of that product. But by the usual rules of logarithms, that's equal to the sum of the logarithms. And so with our definition of entropy, then we see that the entropy is additive. The entropy of the total system is equal to entropy of the left plus the entropy of the right. In thermodynamics language, we often use the word extensive to refer to this additive property of entropy or energy. So things like entropy and energy, we say they're extensive because the total is the sum of the parts. Okay, so this will be a very useful property going forward. We don't need to know about the microscopic definition to make use of this idea that the entropy of the full system is the sum of the entropies of the parts. Okay, here on this slide, I have the main formula that you're going to be using when you're actually doing calculations involving entropy. And so while we have this microscopic definition of entropy in terms of number of microscopic configurations, it turns out that in order to calculate, say, the change in entropy of a part of a system during a thermodynamic process, all we need to know is how much heat flowed into that system and what the temperature of the system is during this process when heat is flowing in. So there's a basic relation that the change in entropy is equal to the heat added divided by the temperature. And that's going to be our central formula for calculating entropy changes in thermodynamic processes. So this looks very different from the other definition of entropy that talked about the logarithm of the number of configurations. But it turns out, amazingly, that you can derive this relation based on that microscopic definition. And it's a little bit mathematical and not essential for what we're going to do with entropy. So I won't talk about it in this lecture, but I've made a special bonus video where I explain this in some detail. So I definitely recommend you have a look at that video if you're interested in how you go from the microscopic definition of entropy to getting this relation between the change in entropy and the change in the heat added and the change in temperature of the system. Okay. So one question you might have is, what if the temperature changes during the process? What temperature do you use in this formula? And so that's a really good question. And to understand it, we have to go back to think about what we did in the case of work when we had W equals P delta V. What did we do in situations when pressure was changing? And the answer was that we needed to break up the process into many parts and then calculate the work for each part during which the pressure wasn't changing very much. So similarly, when we have situations where the temperature is changing during the process, what we need to do is break it up into many parts, calculate the entropy change for each of the parts where the temperature is approximately constant, and then add them up. And so in some cases, when we need to do that, the mathematics that we need to use is, again, some kind of integration. So we'll see some examples of that. But in simple situations, we can have that the temperature is just constant. Okay, so that was a lot of talking so far this lecture. And for the rest of the lecture, I want to give you various questions where we'll apply what we've learned about entropy. Okay, so the main things going forward we need to understand are that entropy is additive, that entropy is something that is determined by the properties of a system at a given time. So once I know the various macroscopic variables, pressure, volume, temperature, I can determine entropy from those in some way. And then this quantitative relation that allows us to calculate entropy based on the amount of heat that flows into a system. So here's an example where you get to use that formula and your understanding of entropy. It's a hypothetical situation where we have 1 joule of energy flowing from this 100 Kelvin object to this 400 Kelvin object. And we want to calculate what is the change in entropy for the full system in this case. So pause the video and try to work through that and see if you can get one of these answers. Okay, so let's go through this. So in order to actually calculate the change in entropy of this full system, the first thing we're going to need to realize is that we're going to want to break it up into the 2 parts of the system and say that the total entropy is equal to the entropy of the left part plus the entropy of the right part. Okay. So that's important because if we tried to apply this formula to our entire system, well, we wouldn't really know what to use for the temperature. And so we can't really apply the formula. Okay, so what we need to do is actually consider the entropy as the sum of the parts. And then we'll be able to write down using our formula for entropy. So we can say that the change in entropy of the total system is equal to the change in entropy of the left plus the change in entropy of the right. I'm writing the little d instead of the delta because it's just a little bit of energy that's flowing from one side to the other. So we can write using our formula for the entropy change that it's equal to dq left over t left plus dq right over t right. And now we look at the question and understand what the q's are, and we just have to be careful about the signs here. So for the left system, we have heat leaving the system, so that means q is going to be negative, and so we have minus 1 joule as the dq for the left system. We take that, divide it by 100 Kelvin, and that gives us the change in entropy of the left side. On the right side, we have plus 1 joule, and then divided by 400 Kelvin. And if we work out those numbers, then it ends up adding up to 0.0075 joules per Kelvin. So overall, what we found is that the answer is B, that the total change in entropy for this process is minus 0.0075 joules per Kelvin. But maybe we're confused now because didn't the second law of thermodynamics tell us that entropy should always increase or stay the same? Second law of thermodynamics says that the total entropy of a system should never decrease. So it appears that this situation in the question violates the second law of thermodynamics. And that's actually true. It is violating the second law of thermodynamics because this situation is physically impossible. So here we actually have heat flowing from a colder object to a hotter object. And that was the thing that we said would never happen. Even though it doesn't violate energy conservation, it's just way too improbable for this to happen during the random transfers of energy that happen in one of these systems. Okay, so our result that the total change in entropy is negative is consistent with the idea that this is a process that can't possibly occur in real life. Had we done the other thing, so had we calculated the change in entropy for heat going from the 400 Kelvin side to the 100 Kelvin side, then the signs of our Q's would be opposite, and we would have got the other answer that would be D. And that would show us that in the other way that heat would be flowing, we would have an increase in entropy. And so that would be consistent with the second law of thermodynamics. One interesting thing to point out in that consistent situation is that the entropy of the right-hand side would still be decreasing. The entropy of the left-hand side, would be decreasing. The entropy of the left-hand side would be increasing, but the total entropy increases. So it's okay if the entropy of a part of your system decreases. That's okay with the second law of thermodynamics, as long as the total entropy of your system increases. So let's go ahead and do another example. So there's the second law again. In this case, we're going to start looking at the change in entropy for various processes in a cycle where we have an ideal gas going through an adiabatic compression and then an isothermal expansion and then a constant volume cooling. So we'll look at the various steps of this cycle and then analyze whether the entropy increases or decreases or is constant, and we'll try to calculate the entropy for these various situations. So take a moment to think about this first question, which has to do with the adiabatic process from C to A. Okay, so this one is pretty easy because in our formula for entropy, the change in entropy for any part of the process is equal to the amount of heat that flows into our system divided by the temperature. But in an adiabatic process, the amount of heat that flows into the system is equal to 0 by definition. And so what we can say is that in an adiabatic process, the entropy is constant. And so that's kind of nice because previously we talked about constant temperature, constant volume, constant pressure processes. And then we had this one weird one, the adiabatic process, where up until now, we didn't have any particular quantity that was remaining constant during the process. Now we can say that for an adiabatic process, it's the entropy that remains constant during the process. So it's a different way of characterizing adiabatic processes. Before we said those are processes where no heat enters or leaves the system. And now we're saying, well, these are processes where the entropy is going to be remaining constant. Let's move on to the next part of our cycle, the step from A to B, and see if you can calculate what the entropy is in that case. So take a moment and pause the video, and then we'll talk about the answer. Okay, so this one is also relatively easy. So in the isothermal process, we have a constant temperature during the entire process. And so our formula for entropy, that ds is equal to dq over t, well, we can actually promote that to a formula that talks about the full change in entropy for the whole process. We can say that delta S is equal to delta Q divided by T, okay, because T is remaining constant during that whole process. And so in that case, we can see fairly easily then that the change in entropy for the process from A to B is going to be equal to Q over T, because Q is the amount of heat that enters the gas during the entire process from A to B. So we didn't have to do anything funny. We didn't have to do, say, some integration because the temperature was not really changing. Or we did do integration, but it was really easy. Okay, well, before we do talk about the last process from B to C, I'm going to give you this question. Okay, so we could calculate the entropy change from B to C using our formula, and we'll actually do that in the next question. But I want to give you a different way of thinking about this based on understanding what is the entropy change around the entire cycle. So we've already calculated the entropy change from C to A and from A to B. And so if we can understand the entropy change around the whole cycle, then we could also figure out what the entropy change from B to C is. So take a moment to think about this. Think about what the definition of entropy is, what kind of a quantity it is, and then see if you could understand whether the net change in entropy around the complete cycle is positive or zero or negative. Okay, well, the answer is that the change in entropy for the complete cycle is equal to zero. And it's the same reason why the change in internal energy around a complete cycle is equal to zero. It's because the entropy is a state variable. So the entropy is something that's determined by the configuration of your system at a particular time. So if we know the volume, the pressure, and the temperature, then we could figure out in principle what the entropy is, because going back to the microscopic definition, it's like the number of microscopic configurations of the system that would have those macroscopic variables. Okay. And so if we start at point C and then come back to point C, well, we're coming back to a configuration that's the same as the one we started with. And so the entropy has got to be the same as the entropy we started with. And so the change in entropy around that cycle is going to be equal to zero. Okay. So just summarizing on this slide, entropy, like pressure, volume, temperature, and internal energy, it's something that just depends on the properties of your system at a particular time. In order to figure out the change in the entropy or any other state variable, you just need to know what it is at the end and what it is at the beginning. And it doesn't matter which path you take, then the change in the entropy is going to be the same for all of them. Okay, so it's the same for all of these three paths from A to B. And if you have a complete cycle going from A back to A, then the change in the entropy is going to be zero, because it's just the final entropy minus the initial entropy. Okay. So that's going to be true for any cycle you can imagine, that the entropy of your gas in the process is always just going to go back to what it was at the beginning. Okay. And so in this process, it stays the same, it increases, and then it decreases. And again, I want to emphasize that that in itself is not any kind of violation of the second law of thermodynamics, the fact that it decreases there in the last process, because what the second law of thermodynamics says is that the entropy of the entire system, including our gas in the cylinder and the environment, that must always stay the same or increase. And so when you have one of these cyclic processes where we say the entropy of the gas in the cycle in the cylinder is the same at the end of the process as it was at the beginning, well, usually actually the entropy of the entire universe, the gas plus its environment, usually that increases. And it's actually only in special situations where the entropy of the gas in the cylinder and the entropy of the environment doesn't increase. And so those are special situations that we call reversible processes. Okay. And so the last thing I'll leave you with here, or maybe we'll work through it. Here's an extra problem, which is basically, what if we directly wanted to calculate the change in entropy from B to C using this formula? So we kind of have an indirect way of calculating it. We realize that the change in entropy from B to C must be negative of the change of entropy from A to B in order to bring it back to the original situation. But what if we just wanted to calculate it directly? Suppose we have 1 mole of an ideal monatomic gas, and it's cooled from 300 Kelvin to 200 Kelvin. What is the change in entropy in that situation? So take a few minutes to think about that. And it's a trickier one than the ones that we've talked about so far, because this is a situation where the temperature is actually, the temperature is actually changing. So to understand it, we're going to need a similar method to what we used for calculating work when the pressure was changing. So let's have a look. Okay. So what we need to do is to imagine breaking up the process into, into many steps, because the temperature is changing throughout the process. And so we can say that for each little part of this process, the change in entropy is equal to the heat that flows in divided by the temperature at that time. And so because it's constant volume, what we know is that the heat that flows in, we can write it as NCV delta T, because there's no work being done. And so the first law of thermodynamics relates that heat to the change in internal energy. And so we have that the change in entropy is equal to NCV dt divided by T. And that's true for every little step of the process. Now to figure out the entire change in entropy from the original temperature of 300 to the final temperature of 200, what we want to do is just add up all of those changes in entropy. And that means we integrate from the initial temperature to the final temperature this quantity dt divided by T. So we're adding up this quantity dt over T for all of the different steps. And that gives you an integral. And mathematically, that's the same kind of 1 over x integral that we had when calculating work for constant temperature. So the answer is a logarithm. So we have NCV, and then the answer is the logarithm of T going from the initial temperature to the final temperature. And if I give myself a little bit more space there, then we get NCV log T final minus log of T initial. And then using the property of logarithm, we can say that's NCV times the logarithm of T final over T initial. Oops, sorry, that's not totally clear, but hopefully you can see that now. Okay, so let's plug in the numbers. So it says we have 1 mole. It's an ideal monatomic gas. So 3/2 R, and then log of T final, 200 over T initial, 300. And so you can work out what that is by plugging in the numbers. Okay, so that's all for today. You might be wondering, like, why we even care. Why are we calculating entropy? What's the practical application of it? And so what we'll see next time is that there are many situations where thinking about entropy can actually help you understand something like engine efficiency in a much simpler way than we've talked about previously. Okay, so that'll be the subject of Friday's lecture, and we'll see you then.